at last. This one here is very similar, except that we have to take one extra parameter. We want to know what that new node, what that new last node is going to store. So we're going to create a new node right here. That one there is going to store E, and then we want to make sure this will be the last node. That means, for example, the tail is now going to point there, and also this old tail, the next should really be pointing to this new tail, right? That's what we should do, roughly speaking. But let's see how we can do that. Also, it doesn't sound like it's going to be a linear time operation. It sounds like a constant operation, right? Let's see. Let me just make one more note here. You want to make sure all these three attributes will be updated properly, consistently. That's something we're going to make sure at the end. And at the moment, size should be 3, right? Let's also make sure we do that. Okay, boundary cases. If I want to add a last node into the chain, definitely I need to worry about when the list is currently empty. Because if the list is empty, adding a last node to there, I got one node only in the list. So both the head and tail should be adjusted to that particular new node. And in the case where size is equal to 1, it's not a special case anymore. I can just handle all the cases where size is larger than or equal to 1 in the same way. Okay. Let's see. So if the size right now is equal to 0, unlike the remove first where we're going to throw some exception, we do something different, right? It's a different operation. What we'll do is like this. Let's start with the empty list first. Let's say the current list is actually empty, meaning that the head and tail will both be null. So singly linked list, we got the head, we got the tail, and we got the size right here, all right? And the size currently is just 1. Oh, beg your pardon, 0, right here, 0. And the head and the tail are both pointing to just null. This is before the addition, before that. After the addition, let's say we are creating a new node right here. So that's going to be a new node. We got elements, we got next. That's going to be the only node, so nothing further in the chain. So the next reference will be just null. What about the element? It's going to be storing E. So whatever E is pointing to is going to be some string. The element just going to be pointing to there, right? You know how to achieve that by some very simple variable assignment. Let's now talk about how the at last is going to change the structure, right? Having only this node in the list, we are going to make sure the head and also the tail both point to the same node, right? Only one node in the chain, in the list. And also make sure we increment the size from 0 to 1. So these are the 3 things you got to do, all right? All right, so you're going to translate that into Java. For the general case, we're now going to assume the size will be larger than or equal to 1. The size will be larger than or equal to 1. And one example will be just this list right here. Right, we got 1, 2, 3, right? Definitely it's one of the general cases. Let's see how we can add last. Step number, let's say 0, okay? Step number 0. Step number 0, we're going to create a new node right here, right? 0. So it's going to be a new node object here, okay? And then the node is going to be very, very similar to what I drew earlier. The elements and the next. So the element is going to point to wherever the parameter E is pointing to, right? It's the same string. And then the next will just be null. Step number 0 to start with. Step number 1. We already have the tail reference right here. This is currently the last node. It will only take a constant amount of time to get attribute access. So once we get there, we should really set its next rather than now to this particular node, right? Good. So let's now do that one. So step number 2 is going to be, step number 1. rather than pointing to null right here, it's now going to point to this particular node. Right? That's step number 1 right here. And then number 2, we can now update the tail. The tail, rather than pointing to here, is now going to point to this new node right here. All right. So now, rather than pointing to here, it's now going to point to this new node. And you can think about that step number 2. Final step will be, since we are adding, so increment the size value from 3 to 4. Okay. This will be step number 3. So ultimately, let's now take a look. We got step number 0, and then we got 1, and then we got 2, and we got 3. Okay, let me just highlight them, just easier for you to see. 1, okay, 0, 1, and then 2, and then 3. And again, each one of them does not seem to depend on the input size. They're just simple arithmetic, like a simple variable assignment to change the references, right? All are variable assignments. Okay, so big O of 1. Also constant operation. All right, so we have seen 2 operations now. They're pretty fundamental, very important. One is about adding a last node. The other one is about removing the first node. We also talk about add first. If you think about it, are we missing one scenario? We talk about add first, remove first. Add last, remove last. We haven't talked about it yet. All right, so here's one question for you to think about it. Just keep the answer to yourself just for now. If you go back to the slides, slide number 23. What's really missing here, which we will talk about today, is about how we remove the last node from the singly linked list. It turns out this operation here is fundamentally very different from all the other 3. It's going to be much more costly to do so. But before we explain why it will be the case, we will have to somehow talk about some other operation which will help us as a helper method, right? So just keep in mind, the remove last is really going to be the bottleneck for singly linked list. And the short answer to explain that is because we only got the next reference. We don't have anything to go to the previous node. And that will be the motivation for having something called doubly linked list, which we will talk about on Thursday. All right, let's now move on. And we'll get back to this question in just one moment. Okay, let's get to something that's going to help us to really implement the remove last a little bit later. Let's say we have a list that's arbitrarily long, and we actually want to access the middle. And the middle, I meant, it can be some index I. And there is one important assumption we are making, right? Right here. I may be 0, that's the smallest value. So we are adopting the indexing notation for array. If I is 0, that means we want to get a first node. If I happen to be list.size -1, that means we want the last node, right? Or any node in between. And of course, at the end, we're going to figure out how efficient this operation is. All right, let's now take a look at, we got the solution right here. I'm going to explain that, and I'll do a little bit of tracing here. And then we're going to do some asymptotic analysis at the end. All right. Let's now start with the method header. Get no add is the method name. Parameter just 1, integer I. And we are making the assumption that I is going to be between 0 and the size -1. 0 less than or equal to I, and less than or equal to list.size -1. Or you can think about n-1. N is always representing the size of the input, right? So this assumption here is very important to remember, all right? Right here. And you can see that there is one if branch right away. If I is either too small or too large, right? If that's negative or it's simply equal to size, there's no such valid index. In that case, you're going to signal some error, maybe throw in some exception. I'll leave the detail to you. And if you look at this particular example list, the size is 3. So conceptually, you can think about 0, 1, and 2 are the indices for each node, right? So when you got three nodes in total, the maximum index you can call will be index 2, right? Just like array. Nothing tricky. So we're going to look at exactly this block of code over here to see how we can compute somewhere in the middle. Since we're dealing with a singly linked list, the only way we can go over the list is from left all the way to the right. Okay? So we start from the head and go all the way to the end. Pretty much like how we computed. In a way, it's very similar to get a number of nodes in the list. But now we don't really have to always go to the end. It really depends on how large I is. If I happen to be 1, then we'll stop here. If I happen to be 0, we got to stop here. If I happen to be 2, of course, we got to go all the way to the end. Right? It really depends on I. So the asymptotic upper bound at the end is going to depend on the value of I, which we'll see. All right? But let's now do a little bit tracing to give you more insight. Before the loop, before the very first iteration, we're going to get 1 here and 1 here, right? So these are the 2 lines we got to execute. We are now encountering, again, a pattern where we got 2 variables that's going to be updated, somehow kept in sync. We got 1 integer there, like an index, pretty much like a size variable that we did earlier. And also we got a current, which is like a loop counter for singly linked list. Let's see how they are going to be updated. So I'm just going to put index here. So index in the beginning is just going to be 0. And the current is just going to be the current head, right? So current head is right here, so current should be here, right? So this is the current. And which will be Allen. So in the table here, I'm also going to trace with you so we can see easier about the asymptotic upper bound a little bit later. So current now is pointing to Allen. And the index is 0. And to know whether or not we should really go for the first iteration, we should really check for this while loop, right? Just something an aside. Whenever you're seeing a while loop, it's always useful to really think about not just about whether this condition is true, think about when it becomes false, so you will know when to exit from the loop, right? Let's say for this condition specifically, we know that as soon as the index gets to the value of I, we're going to exit from the loop. Right? Exit when I is exactly equal to, index is equal to I. When index equals I. That's also something very important for you to always think about. When are we going to exit from the loop? Right? Keep in mind. All right? All right, let's now keep tracing. Since we now, so index right now is 0, so 0 less than 2, true. So when we evaluate this condition for the first time, it will be true. So we should go for the first iteration. So when we go for the first iteration, well, actually for every iteration, we're going to execute these 2 lines, line number 7, line number 8, right? So what we do is we're going to execute these 2 lines right here, right? So for the very first iteration, okay? So index and also current are going to be modified. Okay? For index, it's going to go from 0 to another value. And the current is going to go from currently Allen, right? Allen here is going to be go to somewhere else. All right, let me change the color here. 0 to 1 and also Allen to Mark. Diagrammatically, 0 to 1 because of index plus plus. And when you execute this one here, current, rather than pointing to here, is going to point to current dot next. Right? That's basically what's going to be done by the first iteration. Right? Very easy to see. Okay? All right. Now that we got these 2 updated values, we're going to evaluate this condition here for the second time, right? Line number 6. Should we go for the second iteration? So current right now is pointing to Mark. Index has been incremented to 1. So we're evaluating 1 less than 2. Indeed, it's true. So we should really go for the second iteration. So for the second iteration over here, oh, by the way, I forgot to mention, when we are tracing now, we are assuming that I is equal to 2, right? Sorry, forgot to mention. I is equal to 2, just for now, right? Of course, you can try different value to also verify. When we execute this block of code for the second time, we're going to execute this line here. Oh, sorry. We're going to execute this line here and this line here, right? So index is going to be changed from 0 to something else. The current is going to be changed from mark to something else, right? If you look at that, index is going to be changed to 1 to 2 because you got index plus plus. And then for the current, it's going to be modified to its next, right here. So from, sorry, not from 0 to 1, I beg your pardon, it should be from 1 to 2. Typo. It should be from 1 to 2. And should be from Mark to Tom. All right, so that's going to be done by the second iteration. It seems like we are very close to the end. Let's move on. And we're going to check the condition at line number 6 for a third time. Should we go for a third iteration? Right? So now the current is Tom. Index is 2 right here. So now when we evaluate 2 less than 2, turn out to be just false. That means exit. So no third iteration. So it turns out we only run for 2 iterations. For each iteration, it only involves line number 7, line number 8, about updating the index and updating the current. Each one of them is just constant time operation, right? One very important insight for you to see, right? You can see when index is equal to 0, current is pointing to node at index 0. When index is equal to 1, current is pointing to the node at index 1, and etc. That's how the 2 variables are kept in sync. All right? That one I can write here. Current always reference the node store at index, right? The value over here. Can be index 0, can be index 1, can be index 2, right? It's a very important property just for this particular loop, right? You can also verify. What about asymptotic upper bound, right? We know that for every iteration, it's going to be constant amount of time. How many iterations do we have? In this case, 2, right? Let me just box it. So if you look at just this part here, we got 2 iterations. 2 simply correspond to the value of I, right? So what we get eventually will be the number of iterations will be corresponding to just the value of I. But you cannot say big of I. It's not good enough. In order to figure out, okay, so when we say big O of I, it's a good starting point, but you want to think about what's the worst case for I. The larger the I is, the more iteration we're going to run. The largest value of I will be list.size minus 1. All right? List.size is simply n. Okay? Big O of n minus 1, which will be just big O of n. So it's a linear time operation. Another detail to add very quickly. You might be thinking, well, why would this be the worst case when you say n minus 1? Because if that is simply n minus 1, I can simply use the tail reference. To some extent, I agree with you. If you can somehow modify your code such that you might say, if the I value happen to be list.size minus 1, I'll simply return the tail. In that case, yes, I agree with you. That's not the worst case anymore. But even that, the worst case will be if I is simply equal to n minus 2. It will still be a linear time operation, I'm afraid. right? I'm going to write it down for you. There could be some confusion for you, from you as well, like a morning, fellow students. Okay, so here, excuse me, to access the second last node, you would say get node at. Well, so what will be the I? You can simply say the number of nodes minus 2. Right? In this case, you still get big O of n. Still the same. All right? But if you want to add a special case to say you want to return a tail when I is equal to n minus 1, feel free. Not a problem. But I'm just telling you, ultimately, the running time for accessing the middle will still be linear time. No way around. Okay? All right, any question? Yeah?
So, like, since we're trying to access an element in the middle,
Yep.
that's why we are keeping a record of the index. But otherwise, in the simply linked list, we don't.
Yes, exactly.
Like,
So
we keep record of the size, but not the particular index.
exactly. So let me generalize your fellow student observation a little bit, just to make it a little bit more useful in general. I would say almost for every linked list algorithm you want to implement, any non-trivial one, you always should have at least the current to know where you are from left to right. Any additional variables you might have may have to do with what the output should be or what the input is. In this case, because I know the input is actually some I that I want to get into eventually. So I want to start the index with 0 and getting closer and closer to that particular I value. That's why I need a second variable, right? I wouldn't, you'll be very weird if you only got a current only for the algorithm, either because the algorithm is very simple or you simply got it wrong, right? You always need at least one variable, okay? All right. Guys, I would suggest we do a little bit more and then we'll take a short break, right? We still got 22 minutes, okay? We can definitely do more for today. And by the way, there's a button here. There's always a question here. Since we are trading the space for time, you always want to ask yourself, should we update the tail and size? In this case, no, because it's an accessor. It doesn't modify the list structure. So the answer should be no, right? No here. All right, let's now move on to the next one. All right, so this one here, you want to get a node at right here. And very quick check with you. If I want to do the corresponding operation, well, we talked about the worst case already, right? If I want to do the corresponding operation for the array, I want to get somewhere in the middle of the array. What will be the running time? Constant, right? Array indexing, very cheap, right? Always do the comparison. Right? That one I'm pretty sure you know already. Just always remember. I'm going to put a table on the screen in the beginning of Thursday when we talk about, once we finish the last bit for the singly linked list. You can see exactly how to compare array and singly linked list. All right, let's do this one quickly. Okay. Now we are facing a similar problem here, but now we do want to modify the chain of nodes from the head. Rather than accessing the middle, we want to insert into the middle. It's a way more complex operation, all right? Not really way more complex, just more complex, okay? And before we see the code, Ed, I would like to maybe sketch what you should really do very quickly, diagrammatically. And we'll take a short break, and then we'll come back with the Java code, okay? Let's take a look. All right, so the method we are looking at is something called add at, rather than get no add. It's different, right? It's a mutator. I just didn't really kind of bother to really put the fact that it's actually a void method, but if you like, I'll definitely put it. Okay, it's a void method, doesn't return anything. Okay, and first thing to note, we got index I right here, right? That's one of the parameter, integer. And then we're only considering this particular general scenario. By the way, I could be equal to size. What does that mean? When I is equal to size, that means we want to add the new node as the last node. Think about when I is equal to size minus 1, it's going to be the last index. But if I say I is equal to size itself, that's going to be 1 after the existing node. So that'll be where the new node should go, right? So when I is equal to size, well, let's say this. Let me just give you a quick example. Let's say in this case over here, I got the size will be 3. If I say add, for example, 3, what does that mean? I want to add to index 3, which currently doesn't really exist, but conceptually, I want to add a new node such that it becomes index 3. That's what it means, all right? And similarly, if you actually got I exactly equal to 0, that means you want to add it as a first node. That's just like add first, which we can call that as a helper method. So that's why I don't discuss it over here, right? So what you can think about is when I is equal to 0, it's already considered. When I is equal to 0, it will be just calling add first, which you will see in the Java code later. Let's now talk about this particular parameter more. Okay, it is very important for you to know the following. What we are given is something very minimum. We are not given any node reference. We're only given where we want to insert the node into. Right? Only the index. Only given the index. Not any node reference. All right, a very important observation, but I'll show you why. It will just make our algorithm more costly. Because any node reference we might need in the list, we got to calculate it ourselves. And the calculation turns out to be quite costly, not just constant. Right, we'll see that. All right, so this is how we can understand it. So the I here is right here. Oh, sorry. So think about we got some general chain of nodes right here. Let's say this is index I. So this is the input. Okay. This is the one of the only inputs we got. I. Right here. Okay. So this is the method input. Okay, that's a method input. And then we want to see how things are going to be changed. But let's do step by step. Okay. First of all, let's create a new node first. The new node that we want to insert is going to store E. Can be any string. Okay. Let's say E is already pointing to some string. The new node is also going to point there by its element attribute, right? So let me move this a little bit right here. Okay. So let's create a new node. That'll be the first step. And then we'll talk about the later step. So this is the node that I want. It has the elements, and also it has the next. The element should just be pointing to, should just be pointing to wherever the E is pointing to. And notice that E here is just the other parameter, right? And the next, let me just start it with just being null, just for now. That's a new node. So this will be step number 1. I'm just creating the new node right here. Okay, and I can also give it a name. Let's say N right here. First step, very straightforward. Before I actually talk about what a costly operation is, let's kind of imagine what's going to happen here, which is very critical. I want to somehow insert this node at index I. What does that mean? That means after the insertion, this node should be at index I. Right? That means you should really count after I minus 1. All right? So I'm going to write in a different color. After the insertion, this node should be at index I. This node remain to be at index I minus 1. What used to be at index I should now be I plus 1. Very important, all right? So now this one here should be I plus 1 after insertion. insertion. Okay, I will be also after insertion. And for this index here, it doesn't change. All right. That's conceptually you want to know first. And given that we know that I here should be at index I. So this I minus 1 node should really point to its next rather than here. You should really point to right here. Agree? And then this node here at index I is next rather than pointing to here. You should point to what used to be the index I. All right? I'm going to show you how you can do that, but just one more thing to say. You can think about we are basically shifting all the nodes starting from here to the right by one position. From index I to index I plus 1, from index I plus 1 to I plus 2, and etc. Right? That's another important observation to make. So think about here. We basically shifted to the right by one position. Right? Before I talk about that very costly operation, just remember the most important insight for you to see is about how the indices for the different nodes are going to change, right? Before and after the insertion. That's really the main insight you want to get. All right, let's now talk about how do we do the operation. We only give an I. And somehow we want to make sure this is going to point to here, and this is going to point to here. Unavoidably, we need to get the reference of some nodes. I got two options for you. All right? Either I can simply get a reference for this particular node. I can say get node at I minus 1. Right? Or I can try to say I want to get this particular node. Before the insertion is simply I, right? Don't forget, before the insertion. I can also try to say get node at I. Of course, I can get both, but let's try to keep the minimum necessary. This is this orange one is option number 1. This red one here is option number 2. In order to do this assignment over here, which one do I need? 1 or 2? 1? Okay, good. Now grammatically quite clear, right? Because if you got this one here only, you still don't know what this one is. Right? Agree? Guys, very important insight. Because for the singly linked list, if you get a reference to this node, there's no way for you to go back and see what the previous node is. That's singly linked list. But for doubly linked list, you can do it, which we'll worry about on Thursday. All right? So it turns out step number 2 would be this. We're going to call that method there and say previous assigned to the return value, right? We assume we know get no add already, all right? And then I'm just going to write down explicitly, if you try to call this one here, it's going to be useless, just not useful. You just don't need it. Useless for our purpose of this algorithm here. All right, pretty good. So that will be step number 2. What about step number 3? Step number 3 will be we can now try to do some reassignments. Okay, so now we can say now n, rather than pointing to now, is actually going to point to right. Okay, let me just try this. It's going to point to this particular node right here. Right, so that'll be step number 3. Now, already code for you. So n the next will just be previous the next. Okay, let's take a look. And the next is now going to point to the node that corresponds to the previous, which is this node, the next, right? That's what we're doing. That'll be step number 3. And step number 4, we are just going to make sure this here is also pointing to here, right? Step number 4, we got to make sure this way. So we can say previous the next will be assigned to n. Step number 4. Okay, 4th step. Let me highlight them, and I'll show you what the structure looks like after the insertion. Okay. So we got basically 4th step. We got step number 1, and 1 here, and then 2 here, 3 here, and 4 here, right? And for the node structure, it goes like this. So we start with this node here. Start with this. That one there point to this node. That one there point to this node. And then we also got before and after. So the chain of nodes still is okay, right? Just adding one more node. This kind of conceptual level work is very important. So once we see the code, it does exactly that. Okay? So we don't need to do too much tracing afterwards. All right. If no further question here, why don't we take a short 2 minutes break and then we'll take attendance. Okay. So let's now continue with a new example. Well, actually the same example. Before the break, oh, sorry, forgot to switch. There we go. Before the break, we sketched the idea about how we can insert into the middle at index I. Let's see how we can write a Java code and trace a little bit. Pretty straightforward, right? But let's see some example. Okay. So right here, so this will be the code you have to write in Java. Okay. There will be some special case to deal with. I'll trace that together with you. And you can see that as part of the code for the general case, you have to call get node at I-1 to actually get to the previous node somehow. I'll talk about it. And you can see this step here is going to be dominating, linear, no way around. So this add is going to be linear as well, right? Just because of this step. So this one here is a linear operation, as we know pretty well from the earlier study. This is dominating step. So the whole algorithm is going to be linear. Just keep that in mind. So what I will do is let's now trace the code. So we still got our example list over here with 3 nodes, 1, 2, and 3. So the size should be 3 right here. Okay. And we have already the structure. Remember the add first we did in the beginning, right? Add Tom, Mark, and Alan, right? Alan, Mark, and Tom, right? That's the one we set up already. Let's start with that. We only want to do add 2 calls just to show to you. The first one here is right here. We want to add at index 0. This is one of the special cases. At index 0 means we're going to add first, okay? So what we do is we're going to, the exceptional case is about I being too small or too large, right? You can check the condition. For that, in that case, you're going to throw the exception, okay? So for the first one here, when I is equal to 0, we're going to hit the first case right here, at first. That one there is just going to call at first as a helper method, right? What will that do? It's going to create just a new node that's going to store the string suyang over here. So I'm going to put a node here, elements, and next, right? Let's do that quickly, okay? So element will be suyang over here. And then the next will be null. We'll create this node first, and the add first, which we know pretty well, is going to do the following, right? I'm not going to trace in detail, but what's going to happen is it's going to change the head right here, and then it's going to be changed to this new node. And then the next right here is going to be changed to the old head right here. Of course, the sequence, you got to watch out how you program a Java code. And then we're also going to modify the size from 3 to 4, right? So these are the several steps for add first. So after this, what we will get is we're going to get the head pointing to here, and also the second node is what used to be the head before the insertion. All right, first case. And let's look at the second one very quickly. The second one over here is about adding a new node into index 2. Let's think about what's going to happen here. So we already got index 0, index 1, index 2, right? If I want to add it as the second node right here, what does that mean? That means this is going to be index 2. What used to be index 1 should really be pointed here, and this one should really point to what used to be the index 2, which now should become index 3, right? That's what we spoke about before the break, all right? You can think about it. And let's now try to trace just one line here. And then we'll continue on Thursday. Just one line, okay? So if you look at just this line right here, that one there is going to make a helper method call. And that one there is going to, let me just say the number. lemma 1. It's going to get a node at, so I here is simply just 2. So 2 minus 1 is going to be 1. So we want to get a node at index 1, right? So this will be the node before. Basically, once we got this one here, think about the node before correspond to the previous one that we got earlier at index I minus 1, right? So think about how you may continue by executing 1, 2, and 3. We'll do that in just 1 minute on Thursday. All right, thank you. And now we talk about how you can insert into the middle. That's basically where we stopped from last time. So I would like to continue from here. Before that, guys, any question from last time? Any confusion about singly linked lists in general? So I think today the pace could be slightly faster than before. I do assume a little bit more familiarity about the link structure. Today I'm going to finish off a few more examples on the singly linked list, and then we'll dive into doubly linked list. I really hope to finish everything today. We'll see, but I wouldn't rush. If you really find it too fast, slow me down. That's definitely fine. All right, let's now take a look at this example here, inserting to the middle. All right. So we are basically talking about add at a particular index over here. If I happen to be 0, that means you want to add at the first node, which we traced already, the first node, right? If you see what we did last time, if I did 0 over here, that means add first. What we didn't really trace completely was, what if I want to add maybe 2, right? In this case, I want to add to position 2. 2 here happen to be the end. Well, in general, what if I want to add to the middle, right? You want to think about what's going to happen. Let's complete the tracing and analyze the asymptotic upper bound at the end. So let's say we want to add to position 2, index 2, which will be here. And we want to add a new node called una over here. That's the element, right? So what we do is we know that it's not going to satisfy this special case because the list is not empty. We already got 1, 2, 3, 4 nodes already. So we want to add first, add here, right? So what's going to happen is, if you think about the indices, sorry, let me just get it organized right here. All right. If you want to add at index 2, that means right here. Index 2 is here. That means index 1, which is index 2 minus 1, right? 2 minus 1, like I minus 1. This one here is now going to point to here, so this will be index 2. What used to be index 2 is now going to be index 3, exactly how we illustrated. All right. So the first step right here is to get node at I minus 1, the previous node. This is the most costly step that's going to dominate the asymptotic upper bound, right? So that's what we did last time. Node before is going to be exactly here. Because 2 minus 1, right? It's going to be index 1. Okay. What about second step? For the second step, right here, we're going to create a new node. Right? Let's now write it down. So I'm going to create a new node right here that is going to point to a singly linked node, right? So we got a node here. And we got elements, we got next, right? The element E is una over here, right? Elements, and then we got the string una here, next. And you can see the next will be node before that get next. All right? So that means for this node, we're going to set its next to be node before the next. We're going to set it to be there. All right? So now we're going to set it just right here. So that this is now index 2. And this will now become index 3, right? You can see that right away. So this will be index 2. And now this one will be index 3. All right? Exactly how we discussed it. And then let's do one more step to fix everything. So now node before that set next is going to be the new node, right? We're going to make sure it's also set properly. So node before is right here. The next, rather than pointing to here, is now going to point to this new node right here. And also we're going to update the size. Okay, so the size rather than 4 is now going to be 5. So these are the complete steps, right? You can also trace by yourself. What about the structure afterwards? you can think about it's going to look like this. So what used to be index 1, still index 1. But this now will be index 2, and followed by index 3 right here. All right? And of course, the code itself doesn't really update the tail. You may have to do as well. I got to make sure you extend the code and update the tail also properly. Right? That's something I can leave to you. Right? So that's about insert to the middle. And you just got to remember the asymptotic upper bound is going to be determined by this first step, which is going to figure out where is the previous node. There, in general, it can be very close to the end. In that way, it's going to be linear. All right? So overall, it's going to be linear. Right here. All right, any question about this method here? All right, we're good? All right, sounds good. So now we are done with this method here. Let's see what's next. Inserting to the middle, right? And what about the corresponding operation for the array? If I actually want to insert to the middle of the array, I also need to shift everything to the right by 1 position, right? So that's also linear. So inserting to the middle doesn't really matter if you do it in a link structure or in an array structure. They will just be equally bad or equally inefficient, just linear time. All right? If no further question, let's now look at another one here. What if we want to remove from the end? So this is the remove last operation I was talking about. So this arguably is the most important operation for you to really see why it will be so inefficient for singly linked list. Let's take a look. So we want to remove, we're not creating any new node, just want to remove the last node, the current tail, basically. All right? Now the question is, we already got tail attributes there. We got head, we got tail, we got size. Is the tail attribute itself enough to complete the algorithm? Right? Apparently not. Once we see the diagram, we'll see. All right? Take a look here. All right? Removing the end. I'm only going to trace maybe one line with you just to get an idea. And afterwards, you can try to do others as exercise, right? So let's now see the setup here. So I got basically these lines of code. I build the structure here, Tom, Mark, Alan. So in the reverse way, Alan, Mark, and Tom, right? And then I just want to trace one single line right here. I want to remove the last. And you guys' exercise will be try to trace these two remove last as well to see how they should be visualized and how they should work. That's the important exercise, right? Let's focus on the first one to get an idea. All right, so currently the size, you know what? The diagram should be extended a little bit to really make sure it's accurate, right? So you can think about this guy here. Okay, the size currently is 3. We got 3 nodes. And also we got a tail, right? That's complete. What we want to do is we want to remove this last node here. But the problem is if we want to remove this node, that means we need to set this particular guy's reference next to be null. But do we know what this one is? Not really, because we only know that this guy here is the tail. But what about this guy? We don't have any attributes storing that. So the only way we can get its reference is by computing it using a loop. All right? That's very important for you to see. All right? So this one over here is the second last node. That need to be computed. And we don't have a direct reference to it. And you cannot just say tell the previous. There's no such thing like a previous reference. Would be the case for doubly linked list, but not for singly linked list. Let's now trace it to see exactly how we do it, right? So here, the current size is not equal to 0, it's 3. So we are not going to do this, all right? Also, the size is also not equal to 1. Also, we don't need it, all right? So these two edge cases, we don't satisfy it, we can skip. So what I will do is, let's now do 1 here, 2 here, 3 here, and then 4 here, right? We got 4 steps. Let's execute them one by one. Step number 1. The second last node is going to be computed using get node at, right? We want to calculate the previous node. Right? Size minus 2 is going to give us the index for the second last, right? Size minus 1 is the index for the last node. So size minus 2 will be second last. So what we'll do, so this one here is going to be big O of n, right? You can see that it's accessing the middle, right? So what this one will do is we're going to create a reference right here, and then that one there is called second last node. Right? The current size is simply equal to 3. So 3 minus 2 will be 1. So 0 and 1. So that's exactly this node, right? That'll be the first step. The second step, once we got a second last node, everything else will be straightforward. Second last node that's set next should be null. So second last node that's next should be null, right? So that's the second step. So this was the first step. All right, that one's done. And then we're just going to update the tail. So tail, rather than pointing this node that's being deleted, it should be this second last node. It's not a new tail. So what I'll do is, rather than pointing to here, it's now going to point to right here. So this will be step number 3. And step number 4, we also got to make sure we update the size from 3 to 2. Step number 4. So after all these, what we have is a structure that looks like this. So we got the head pointing to here. Okay, maybe a little bit thinner. We got a head pointing to the first node, and then the second node, and then that one there is simply pointing to null. That'll be it. Right? Any question about this? Okay, make sense? All right. Important exercises for you guys will be to try to trace maybe remove last and remove last, 2 consecutive remove last after that, to see how the list structure is going to change. Important exercise. Okay. All right. Any follow-up about this? All right. And of course, the running time, as we said earlier, is going to be dominated by step number 1 right here. So it's going to be big O of n. Also a very inefficient operation because it involves going to the second last node. No way around, linear. All right, 2 more, and then we can conclude about singly linked list, and then we can move on to doubly linked list. So these 2 exercises over here, it's just about if you want to insert after and insert before, how would you do it? Okay. And these 2 over here, we're assuming that we are basically getting the node reference right here, node here. So give me one moment. Let me just show you where you can see that on the slides. So we are done with removing the last. That one is done. Oh, sorry, right here. If you look at slide number 30, so that's what I'm talking about, right? So we got these 2 operations over here. In the slide, it simply got different steps over here describing in English. But I'm going to tell you how you can think of each step visually. And your job will be to translate them into Java. Right? Similar exercise. I'll rely on you. Let's take a look at one by one. Okay. For insert after, right here. So what we get as input is some node n. Okay, you can see there's a node n. So n is pointing to somewhere in the middle, right? Somewhere. What we want to do is we want to insert a new node maybe after that. All right? That one there doesn't seem to involve anything about previous node. Agree? All you got to do is you got to make sure there might be some next node right now. If I want to insert a new node, you got to make sure I goes this and then go this, basically. Right? That's what I need. So what I can do is let me just put a little bit more in context right here. Let's say we got another node here at the moment. That one is simply just n.next. Right here. N.next. N.next might be null if the n is already the tail, which is okay. This algorithm will still work. Okay? So there will be 3 steps for us to follow. Number 1, of course, we got to create a new node. So number 1, we're going to create a new node right here. And the node is going to contain the elements and also the next. Elements and also the next. You know what? I'll put elements. Oh, that's fine. That's fine. Elements and also the next. The element is going to point to wherever the parameter e is pointing to, right? You can see that's an element, right? What about the next? The next, For now, let's just put let it pointing to null, which is okay, just for now. Step number 1, just create a new node. And then step number 2, we can simply say the next reference here, rather than null, is now going to point to n.next. All right, let's do that. So what we do is we can say rather than pointing to here, it's now going to point to n.next. So this will be step number 2. And step number 3, we can try to say n.next rather than pointing to over here, it will just point to the new node right here. Step number 3. 3 steps. We don't seem to need any of the concept about previous node. So there's no linear operation or like a loop needed. So insert after is simply a very efficient operation, just about point like a references reassignments. So this is constant time, right? Again, we don't need to see the Java code to derive this. All right, question about this. Okay with this? So when we get to the final stage about summarizing the syncly linked list, of course, for all the operation that we have spoken about so far, we're going to put in the table. But if I give you anything like a new algorithm to define for linked list, you also got to think about what kind of cases are they involving. So you can judge whether it's going to be an efficient one or inefficient one. Right? Okay, let's talk about this one here. For this one here, if the node here is referring to this node, right? Let's say the node that's given as arguments is right here. Okay? The idea would be I want to insert a new node before that. That means whatever node that's really currently pointing to it is the next. Rather than pointing to there, it's going to point to here. That one does not seem to be an efficient operation anymore, does it? Not really. Because how do I know this reference here? I'm not given it. I'm only given n. In that case, I need to compute it myself using a loop. But I don't really know what the index is for that one. So I cannot really use get node at. I can still use a while loop. All right? That's a quick sketch. Right? Let's see exactly how we can do it. All right? If you're kind of sketching your mind about how the loop can be written, that's a good sign, but let's see. Somehow, I need to figure out what's the previous node right here, right? So you can think about this is the previous node that I need to compute, right? I'll get there in just one moment. That's one step for sure. And that step actually obviously is going to dominate the running time, as we'll see. All right? All right, let's now take a look. Step number 1, let's just create a new node first. Easy one. So step number 1, I'm just going to create some new node. Let me call it NN, new node, which will point to a new node object right here. And then that one there is going to get elements and next. Elements and next. You know what? Let me just move this a little bit up right here. All right? So the element is just going to point to wherever E is pointing to, right? Remember, E is right here, right? What the other parameter. What about the next? For now, let's make it null. Step number 1, very straightforward, just a new node. Step number 2, I basically have to make sure I got a node reference for the previous node. That's important before I can set this next reference, right? So step number 2, the most crucial step, is about computing the previous node. All right, and we need a loop. As I said earlier, we cannot really call get node at, which expects some integer number. We don't even know where this node is. Of course, what you could have done is figure out what this index is and say that index -1 and call get node at that index. That's fine, but there's a better way. All right. I'm just going to put a star here and then I'll put it here. You might just need to use a while loop for sure. And then remember the current reference, right? Let's say we got a current starting from the head. We want to run the while loop until current.next equals this particular n. Okay, Of course, I really meant to say something like this. Let me explain this. Not equal to. All right? And of course, you have to make sure you say current dot, sorry. Here, you got to do the normal update. You got to say current equals current.next, right? That's a standard updates. But let's analyze this condition here. Why would it work? If you look at this one over here, remember I mentioned last time, whenever you see a while loop, you always want to think about when does the loop exit. So that'll be the logical negation of the Boolean condition here. Let's take a look. That's going to help. So this one here tells you the loop is going to exit when this condition is false, meaning that rather than not equal to, it's going to be equal to, right? When the current dot next equals n. In that way, we know that current is indeed this previous node. Because if current dot next equals n, the current must be the previous node, right? That's how you write a loop. That's another flavor you can also learn. All right. Any question about step number 2? That's the most fundamental step, actually, to make it work. So this one tells you whenever you want to somehow run a loop from the left until certain place for singly linked list, you don't necessarily always have to use an integer to tell you when to stop. Also, you don't really have to say current equals null or not equal to null to stop. This is just another example. It really depends what the problem is, right? So to really think about this one here, think more about the exit condition. This is going to help. All right. Step number 2. And we know that this while loop here, no way around. You may have to just go all the way until the end of the list, very close to the end. Linear time. All right. So this one here is going to be big O of n, because the previous node can be very close to the end of the list. Oh, let me just use this one here. All right, that's step number 2. And step number 3, now that I got a previous node, I can now just do the remaining task, just to set the references. Step number 3, I'm just going to say the new node next, rather than here, is now going to point to the n here. This will be step number 3. And step number 4, the previous node I got, I can now say its next should be pointing to this one here. Step number 4. And of course, at the same time, it's going to reassign this one here. So think about this is like a next. So this next is no longer there. After this, what kind of structure do we have? We have basically this previous node is going to point to the new node, and the new node is pointing to the n right here. So that's exactly insert before, right? We're inserting this new node right before this node here. And that's a linear time algorithm, because the critical step number 2 is linear. All right, any question here? So when you, just before you ask, okay. So when you review these 2 operations, you really want to ask yourself, why is insert after constant, but insert before is actually linear, right? As we explained. Yeah, question?
How do we do if the insert before, you want to insert before the very first node?
Insert before the very first, it will be very similar. So let's say insert before over here. I see what you mean. That will be a special case, right? So here, very good question. So insert before, this is more talking about the previous node happen to be not null. And if you want to insert before, that's even easier. If you want to say, I'll put it here. Insert before the first node. In that case, you can just add first, which we know how to do, like an edge case. Good. All right, guys, any question about this? Good. All right. So we are done with all the operations that I want to discuss about singly linked lists, but let's now take a very quick look on some exercises I want you guys to also try. Of course, these 2, you want to put them into Java code. And also this one here, you can think about how do I implement remove at. All right, I want to remove the node at index I. Sounds like a linear time operation because there's no way around. I have to get to some node in the middle. But should I go to I minus 1 or should I go to I? You guys decide. Okay, think about it. All right? Given all the operations we have said so far, it should be possible for you to judge. For implementing remove at index I, for removing a node at index I, should I get node at index I or should I get node at index I minus 1 or some other index? You want to think about that. All right, let's do a very quick comparison and we can take a very short break. Right? Today we can take a few short breaks since there are many things to cover. So I want you guys to reset after some short break. So before the short break, let's talk about this table here. We are going to compare arrays and singly linked lists based on what we have said so far. So should you memorize the result for this table here? I don't think you should really memorize it, but you should really, when you study for the singly linked list, look at this table here, look at the template that's blank, and think about each one of them. Think about the reason for the asymptotic upper bound, right? Which is what I'm going to present right here. Let's first of all think about if I want to get a size or get a first and last elements. In the case of array, pretty easy. Array.length. Also at index 0, at index length minus 1, indexing, cheap, efficient. How about singly linked list? I can get to the size attributes, I can get to the head, I can get to the head, I can get to the tail, right? So all efficient operations. So for this one here, I can simply say big O of 1. That one's easy, all right? And let's talk about array first before, and then we move on to linked list. For array, if I want to get to index I and also, okay, so here when I say remove the last element, let me clarify. What I really meant there is something very simple. So for the array, I really assume we don't do any resizing. We simply say A at index A.length minus 1 will just be assigned to just now without resizing it. Pretty simple operation, right? So that's why it's constant time. But of course, if I tell you that resizing is necessary, it will be linear, right? So for these two, for array, it will just be constant. And if you want to add the first elements, that will involve some shifting, right? All the way to the right by one position. Also, if you want to remove the first element, you're also going to shift everything to the left by one position. So that's going to be expensive, linear time. Add remove anywhere in the middle is also going to cost you linear time, right? So for the array, we said that it's always expensive if you want to touch, somehow get rid of some element in the middle or in the beginning or at the end. Linear time. Let's talk about singly linked list. Whatever that's actually cheap over here turns out to be expensive for singly linked list. For example, if I want to get element at index I, get middle, linear time, right? What about if I want to remove the last element? Also linear, because I need to get to the second last node, right? Big O of n. So for every one of them, we also talk about, so you want to make sure go back there and review the rationale. Why? For example, removing the last will be linear time. And then when we want to add or remove somewhere in the middle, if somehow we can get some reference. For example, let's say here, I want to insert before, but I'm given, I want to insert after. For example, like right here, if I'm given the node itself, I don't need to compute the node by myself. So I'm given, so it will be a constant time operation. It's just all about references, all right? So the critical distinction over here will be, so this one will be actually constant time because I don't need to compute any of the nodes. There's no need to compute the node if they are simply given. On the other hand, if they are not given, then you have to compute it yourself. Maybe the node before, or maybe the second last node, and etc. All right? So symmetrically, it's going to be big O of n. Right, so that's the complete table for comparing. All right. Any question? about this. Yeah, use this table here to somehow summarize about everything we have discussed so far about arrays and linked lists. It's a very nice way to kind of reflect on what we have learned. All right. If no further question, why don't we take a 2 minutes break and then we'll just come back for doubly linked list. Okay. All right. So we are done with the singly linked list, and we're gonna move on. Oh, by the way, slide 33 to 36 about the generics, which I assume you guys have already studied. If you haven't, please catch up. It's required for your programming test as well. Okay. Let me know if you got any trouble following the material I gave to you. All right. Let's now talk about doubly linked list. Before that, let's have a final recap about singly linked lists. Okay. So we pretty much know. Before the break, we actually did the table, but now let's put it in the textual form. So you got to remember what singly linked lists really perform well versus poorly. All right, you can look at the bullet points. We have already said everything. What I want to draw your attention to is about this one here. Whenever you want to insert or delete from the middle, if you're somehow given the reference to the previous node, then good. It's going to be constant time. If you are not really given as a method parameter, then it will be linear time, right? That's something you want to watch out for, all right? And we're going to see that principle about trading space for time one more time to see how we can somehow introduce some additional attributes so that some of these operations right here, some of them, is going to be improved drastically from linear to constant. But I'm not saying that having that little extension is going to magically turn everything from linear into constant. In that way, nobody's going to use singly linked list, right? There's only going to be one or two operations that will be a little bit more efficient, right? That's something we'll see. All right, so we're going to introduce new attributes just like how we introduce size and tell. We'll get there, okay? Let's now talk about doubly linked list, okay? So for doubly linked list, let's go over some visual introduction here. Okay, right here. All right. It is still going to be a chain of nodes, but now the direction about referencing is going to be bidirectional. Rather than just next, we're going to see another reference called previous. And we need to visualize that before we see the Java implementation. So the bidirectionally connected, bidirectional here is very important. Right? So let me show you some very quick diagram. In the case of the singly linked node, SLN, right? I want to distinguish between singly linked node and doubly linked node. Each node has only two compartments. We have the elements, and we also have the next. So there's always single direction. You always go to the right, right? But for doubly linked node, we're going to introduce one more direction, which is conceivable, to the left. So doubly linked node is going to look a little bit like this. A little bit bigger because it stores more data. The convention is in the middle, we still try to put a reference for the elements. And then the next one here is going to be next, going to the right. And the new addition is we're going to have something called previous. Right? PREV. Okay? That one will allow us to travel backwards. Okay? And you can right away imagine if this node happens to be the tail, do I still need a loop anymore to calculate the second last node? Not really, right? I can just go to the previous. That's immediately going to make it from linear into constant. All right? So that's something you want to see right away. All right? So what we get is we got the data object. Okay. We got the data objects that already also the next. So these two are the attributes that are already in the singly linked node. We are making the extension about previous node right here. So that's the extension. Okay. And then let's see a little bit more visualization here. Let's see how the object structure is going to look like. Okay. Let me see this right here. Okay, let me just present maybe a little bit more bullet points from the slide, and I'll do the visualization right here. So we talk about the two references to the data and also to the next node. And also, we got the previous node reference as well. All right, so this is also another important point. So if you want me to summarize about how many extensions do we need in order to have a doubly linked list, 2 extensions basically. The one we just talked about is a previous reference. So here comes the second extension. And the second extension is really because in the singly linked list, we have to deal with edge cases explicitly too often. That will somehow make our code structure more complicated than necessary. So we want to simplify the code structure. Nothing to do with performance, really, but it's good software engineering principle to really keep your code as simple as possible. And let me give you some example. In the case of the singly linked list, let's say at first, right? You actually have to consider if the current list is actually empty. In that case, you have to deal with it explicitly. Tail should be equal to head afterwards. Similarly, let's say you're trying to do remove first. In that way, if the current size is equal to 1, after removing the first, the list becomes empty. In that case, you have to explicitly say the head and tail will be null. It would be very nice if we don't really have to write these two if or else if explicitly. There is a way to achieve that by some small extension in the doubly linked list. We'll see that. All right. All right, let me show you the extension very quickly, the bullet points, and then I'll visualize them. Okay. Header and trailer. All right, so whenever we talk about header and trailer, so these are the concept for doubly linked node. Sorry, doubly linked list, not singly linked list. In the case of singly linked list, we got head and tail. By doubly linked list, we got header and trailer. Right? Notice the difference here. Also, the wording is a little bit different, right? Header and trailer. And sometimes people like to talk about them as sentinel nodes or guard nodes, right? Just terminology, right? But I might just call them header and trailer. So these two do not store data. Okay, I'll visualize it, and also, okay, and etc. They always exist, even in the case of empty list. So now let's clarify visually. Let's now get to visualizing empty list, either singly linked or doubly linked. Let's see exactly how they will look like.